Hi, this is Mr. Flint,
And Miss Segovia.
and we are here to discuss constant acceleration with you. Let's go back and review through some things with acceleration. We need to write a word equation for acceleration. This is found on your note cards. Acceleration is equal to the change in velocity divided by the change in time. We could also write A equals delta V over delta T, which hopefully you're familiar with the delta. Delta just simply meaning change. So here's our delta, and that means change. Okay, so let's take a look at the symbol for acceleration, which is A. Hopefully you know that. And what units do we use? Well, we use meters per second squared. So where does that square come from in the units? Well, let's look at it here. Since acceleration is change in velocity over change in time, we're going to plug in the units for velocity into the change in velocity. So they come up here, and the units for time will come in down here. So basically we'll get the units on top. We could think of just putting in the units up here on top, so meters per second on top, and seconds here on the bottom. And that's all that you see right down here. It's just rewritten nice and neatly down here. Meters per second over seconds. Meters per second per second. So then we can pull this meters per second out of the top and place it here, and pull this over here right next to it. And these two things are equal to each other. They're the same algebraically. So then we just multiply across the top. Meters times 1 gives us meters on top. Seconds times seconds gives us seconds squared on the bottom. So that's where we get those units of meters per second squared. We can also say meters per second, but usually we write it out meters per second per second. These three things are identical. They are all the same thing. It's like saying 6 of one or half dozen of the other. It's the same thing a few different ways. Now, the difference between velocity and acceleration using words rate of change. Well, if we use words for velocity, we would see that velocity would be the rate of change of position with time. So with velocity, we're looking for that keyword position, change of position. And if we look at the formula for it, for velocity, we're going to see change in position, or change in x over change in time. Whereas acceleration, we're going to look at the rate of change of velocity with respect to time. So acceleration, we would see the change in velocity over change in time. All right, and we've gone through those. That's on your formula cards. That's just some quick review. Now, an object traveling forward has an acceleration of 2 meters per second squared. What is happening to that object's velocity? Well, the velocity would be increasing by 2 meters per second every second that goes by. So we could also think of it as it's increasing at 2 meters per second for every single second that goes by, every 1 second that goes by. But a lot of times, instead of writing it 2 meters per second, we'll just write that as 2 meters per second squared. In other words, the object is going to gain 2 meters per second of speed every second that's going by. Well, what if we had an acceleration of negative 3 meters per second squared? What is happening to that object's velocity? Well, you're going to see something very similar. Instead of gaining 3 meters per second every second, now we're going to see it losing 3 meters per second every second. So the velocity would decrease by 3 meters per second every second. In other words, the object loses that 3 meters per second in speed for every second that goes by. Okay, now, with acceleration, you have to remember acceleration is a vector. And how do we determine the direction of acceleration? Well, we have to first look at the velocity of the object. And if the object's velocity, let's say we've got an object, so I'll do a little physics cart, okay? And it's moving here to the right. If that object is speeding up, so here's its velocity, If that object is speeding up, then its acceleration has to be in the same direction too. So let me see here.
Oops.
Okay, let me see
Don't you
here.
love technology when it doesn't cooperate with you?
Okay, so I was going to try and change colors, but it's a little too difficult to change colors on this one. We'll do it hopefully in a future one, but the acceleration is in the same direction as the velocity. That means that the object is going to be speeding up. Now, what happens if the acceleration is in the opposite direction of the velocity? So let's say it's still moving to the right, there's your velocity, but now the object is slowing down. Well, we know that the acceleration would have to be in the opposite direction, okay, the negative direction here. So that would be negative acceleration. So that object would slow down if it was accelerating in the opposite direction of the velocity.
So when you see negative acceleration, it doesn't mean necessarily that it's turned around, it just means like right now it's slowing down.
It would slow down, come to a stop, and then it would turn around, just like a cart on a ramp going uphill. It's going to go up that hill, come to a stop, and the entire time it's going up the hill, the acceleration's down the ramp in the opposite direction of the velocity until it stops. And then it switches, the velocity goes back down the ramp, and the acceleration's down the ramp, and it starts to speed up.
So then they're going in the same direction.
Both the velocity and acceleration would be in the same direction as the cart's going downhill, and it speeds up.
Okay, so
Okay.
we get to do some labs like that later, right?
Yes, we will look at that a little bit later. Now, we need to write the equation for velocity as a function of time for constant acceleration, and here is this equation. Now, you've seen this equation. It's just a rearrangement of your acceleration equation, where we've got the final velocity, sometimes we'll put an F there, minus the initial velocity over change in time. Okay, so let's move time to the other side. Time goes over here, just like this. So acceleration multiplied by time is final velocity minus initial velocity. Now let's get rid of the initial velocity. It comes over here. Okay, so that leaves us with the acceleration multiplied by time plus the initial velocity is equal to the final velocity. But a lot of times we don't write it with the single variable on the right side. We write it with the single variable over here on the left side, and we get this equation up here on top.
It looks a lot like slope too. And velocity is the slope, right?
Yes, velocity would be a slope
Of a distance time graph.
of a distance time graph. Now, write the equation for average velocity under constant acceleration, and we get this right here, this
good
this
gosh.
equation. And all that is, it looks complex, but it actually just makes sense. When we're doing your averages, anytime you do an average, and if you have multiple things, you just divide by the number you have. So let's say you have, I don't know, what are some objects we could have?
Cans of Coca-Cola.
Cans of Coca-Cola. So we've got,
Diet Coke for me, actually.
okay, we got a bunch of Coca-Cola cans, and then
So
we
like-
had multiple ones, and we wanted to do their volume. Okay, so we'd add up the two here, and if we wanted to do an average, we'd have to divide by 2. Okay, so that's all you're doing. It's just taking a simple average. With velocities, you'll have 2 velocities. You'll have a final velocity and an initial velocity, and you just divide by 2. And that gives you your average. Write the equation for position as a function of time for constant acceleration. This one is new. The position is equal to 1/2 AT squared plus the initial velocity multiplied by time plus the initial position of the object. So let's look at one more of these, what we call the no time equation, and it looks like this. The final velocity squared is equal to 2 times the acceleration multiplied by the displacement of the object plus the initial velocity squared. So let's go through all of those variables real quick. You can see them here. X is position, V is velocity, A stands for acceleration, those you already know. X naught is initial position, V naught is initial velocity, and T is time.
The naught is the teeny tiny little zero. on the
That little
bottom.
0. And it just represents at time 0 or at the beginning of the problem, whatever is happening at the beginning of the problem. So this little thing, sometimes we'll call it a naught. just meaning 0,
To
times
be
0.
or not to be.
All right, and then you've seen the guess method. We gave you some examples of those, but here it is written out. You should have this worksheet or skill sheet pasted into the back of your notebook so that you can reference it at any time. The reason why we go through guess is so that when you get to AP Physics or AP Chem, you have a way to do your free response problems and you're used to that and you can get full points on those problems. And yes, we'll eventually be trying to do some of those. Right, now, there are some examples here, and this is part of your notes. Okay, and so you can just kind of pause and go through these things, but they're very similar to the examples that we've already gone through in previous problems. They're just now using some of the newer equations here. And we'll just set these here, and as we get into some of these in the next week, we will give you even some more examples on using these problems. All right, thank you. Talk to you later.